Hello everyone, I'm Songyuan from the Reliable Autonomous Systems Lab at MIT. Today I'm going to talk about our work on learning decentralized stabilizing controllers for network dynamical systems. My advisor is Professor Chuchu, and we also collaborate with Yumeng and Professor Guannan from CMU. Large-scale network dynamical systems play an important role across a vast spectrum of real-world applications, and controlling, in particular stabilizing such systems, has long been recognized as a challenging problem. Here are three typical network dynamical systems: join swarms, where we want joins to keep some formation and finish some tasks; power grids, where we want the frequency and voltage to be stabilized at some preset values; and chart platoons, where we want the charts to drive in some predefined formation. Network dynamical systems are often constructed by many small subsystems. The small subsystems interconnect with each other to form the huge network system. As a consequence, the dynamics of subsystems are not isolated, but can be influenced by their neighbors. This type of systems are often hard to stabilize because first, the state space of the whole network system is so large that decentralized controllers are hard to be applied on it, which we say scalability problem. Second, even if we use decentralized controllers on each subsystem, the number of subsystems can still be so large that we can now design a unique controller for each subsystem, which we say network generalizability problem. And third, the dynamic subsystems can have uncertainties, which is the robustness problem. Considering to stabilize a system, the first thing that comes to our mind could be the Lyapunov functions. Simply put, if we take the states of the whole system as x, if we define a Lyapunov function v that is 0 at the goal point, greater than 0 otherwise, and its time derivative is smaller than 0, then we can conclude that the system is asymptotically stable at the goal. However, it is very hard to find a Lyapunov function for a network system because the dimension of the state space can be very large, like thousands. So, are there any other ways to stabilize the system, better in a decentralized way? The answer is yes. The problem of decentralized controllers is the interconnected dynamics. If some states in one subsystem grow, they can also affect the states of its neighbors, and the neighbors of the neighbors, and finally back to itself. This can cause a vicious cycle and could finally make the whole system explode. But if we think in the opposite way, if after this loop, the states actually get closer to the goal, then the system will be stable. This doubt is similar to the small gain theorem. Based on this doubt, input-to-state Lyapunov functions are introduced, which is in short, ISS Lyapunov functions. ISS Lyapunov functions are introduced by Professor Zhang from NYU. Instead of being functions of the global states, ISS Lyapunov functions are functions on local states of subsystem xi. The conditions of ISS Lyapunov functions are very similar to Lyapunov functions. They should be 0 at the goal, greater than 0 on other states, but the third condition is a little bit different. Instead of requiring their derivatives to be negative everywhere, we need them to be negative only when the value of the ISS Lyapunov function of this subsystem is larger than other subsystems, which means this condition implies the third condition. ISS Lyapunov functions have been introduced for decades. Can it solve the three problems of network dynamical systems? Scalability? Yes, because we now can find ISS Lyapunov functions and the corresponding controllers for each subsystem instead of the global system. Network generalizability? No, because we still need to find the specific controller for each subsystem. Robustness? No, because the ISS Lyapunov functions do not consider system uncertainties. Moreover, ISS Lyapunov functions actually bring in a new problem. That is, how can we find such ISS Lyapunov functions? To solve these problems, we introduce our approach called neural ISS Lyapunov functions, in short NeurIS, to learn ISS Lyapunov functions with neural networks. First, we introduce some new results based on the ISS Lyapunov functions. Let's recall the three conditions of ISS Lyapunov functions. The first two conditions are certainly decentralized, but here in the third condition, the matrix is taken over all the subsystems, which make this condition still depend on the whole system. To make the condition to be fully decentralized, we present in our paper a new result that this matrix only needs to be taken on the neighbor subsystems of I. This makes the conditions of ISS Lyapunov functions only depend on the neighborhood of subsystems, so they are now fully decentralized. Then, do we need to find the specific ISS Lyapunov functions for each subsystem? To solve the problem of network generalizability, we show in our paper that if some of the systems have some similarity on their structures, they can share one ISS Lyapunov function and one controller. So here, these three subsystems can share one ISS level function, and these three can share another one. In this way, the number of ISS level functions will reduce a lot, since real-world network dynamical systems often have similar structures. Finally, we discussed about the robustness of ISS level functions. We proved that if the dynamics of each subsystem is control affine, the uncertainties are inside the convex hull, and the dynamics are affine to uncertainties, then if the ISS level functions and satisfy the conditions on the vertices, they can also be satisfied inside this convex hull. In other words, the ISS level functions will be robust to the uncertainties inside this convex hull. So now, the ISS level functions have the scalability, network generalizability, and robustness. Then the final question is, how can we learn such ISS level functions? We parameterize the ISS level functions and the controllers using neural networks. Remember that subsystems with the same structures can share the same ISS level function and the controller. We only need 2 neural networks for ISS level functions and another 2 for controllers. Then, we need to design loss functions for training the neural networks. Let's recall the conditions of the ISS level functions. The first 2 conditions are easy to design losses, or they can just be satisfied by the construction of the neural networks. But the third condition is very tricky because here is a logical condition, imply. How can we deal with this implied condition? This implied condition can be written as A implies B, which is equivalent to negative A or B, which is also equivalent to the maximum of negative A and B. To make the max of negative A and B to be true, we can directly minimize the loss as this form, which will punish the violation of negative A and B. In this way, we solve the problem of encoding the implied condition in training. We can then train the neural ISS level functions and the neural controllers jointly to get a stabilizing decentralized controller. We conduct experiments in 4 environments, including network microgrids, power grids, charge platoon, and drone formation control. Due to the time limit, we only show the results of drone formation control environment here. In this environment, starting from some random initial positions, we want to control the drones to fly on the grids of a rectangle, keeping the distance the same between each drone, and let the drones track an unknown speed profile. We assume the drones only have local observations of the positions of their neighbors. Recall the 3 challenges of the network dynamical systems: scalability, network generalizability, and robustness. To test the scalability, we train the controllers and the ISS level functions using 4 drones and test the controllers in both the training environment and the environment with 100 drones. To test the network generalizability, let all the drones share 1 controller and 1 ISS level function. And to test the robustness, we model the unknown speed profile the drones are supposed to track as uncertainties. We compare our algorithm with both centralized and decentralized controllers. For centralized controllers, we use the reinforcement learning algorithm PPO, the work of reinforcement learning with the optional created LY PPO, and the neural centralized control optimal function work NCLF. For decentralized controllers, we use the multi-agent reinforcement learning approach MAPPO and the decentralized L2R controller. We first test our learned controller in a 4-drone environment. The drones form the group formation and the tracking error is low. For the centralized neural control optimal function approach, we can observe that it also forms a group formation, but the tracking error is larger than our approach. This is mainly because the dimension of the state space is so large that it is hard to learn a robust centralized control optimal function. For centralized RL algorithms, PPO cannot form a group formation, and LY PPO fails on this test. This is because PPO cannot ensure the stability of the learned controller, and LY PPO needs to learn a centralized optimal function along with the RL policy. But fitting a centralized optimal function in a large state space is hard, and a bad optimal function can lead to worse RL behaviors. For the decentralized approach MAPPO, its behavior is similar to the centralized PPO. L2R behaves good on keeping the formation, but it has large tracking errors. This is because L2R is designed for linear systems, and its performance is hard to guarantee in complex nonlinear systems. Then, we test the scalability. We directly apply the learned controller to an environment with 10 by 10 100 drones. One can observe that our approach forms a group formation, although the distance intervals are not exactly the same because the drones can only observe their neighbors. All they can do is to keep the distance to the left, right, upper, and lower drone to be small, but the error of the distance can still accumulate. We can also notice that the tracking error of our approach is small. Then we test two decentralized approaches, MAPPO and L2R. The behavior of MAPPO is similar to the 4-zone environment, but the tracking error becomes very large because each zone only has local observations and the error can accumulate. The behavior of L2R is good, but because of the linear, nonlinear depth, the power of keeping the formation and tracking is not as good as new rays. Our algorithm solves the scalability, network generalizability, and the robustness problem of network dynamical systems, but we still have these limitations. First, we need the knowledge of dynamics. Second, our results on network generalizability requires structural similarity of the subsystems. Third, our robustness results needs the dynamics to be disturbance affine and the disturbance to be convex. And finally, it's very computationally expensive to verify the learned ISSM functions because neural network verification is an NP hard problem, so we didn't do it in our paper. Finally, here are our contributions. You can scan this QR code to reach the project website for more information. Thank you.